Good afternoon, everybody. I hope you enjoyed lunch, had some time to play with the puppies, enjoyed the fireside chat with Andy Jassy, some great information in there. Got a little preview. There's all kinds of neat equipment that are starting to be set up in that room for the party at the end of the day. Looks like we're going to have some circus acts and things. It looks kind of fun. So thank you for joining us this afternoon. A few housekeeping items. Emergency exits are behind me here to the left, behind you, straight out. In the event of the emergency, please do not get in an elevator. Please go down the stairs and get out of the building quickly. If you haven't already, please download the app. There's a web-based app for Android phones and then an app available in the App Store for iPhones. We kindly request that you submit feedback for all of the sessions you attend. We comb through that information meticulously to help us better prepare for future events, so please take the time to submit feedback. Should you need a bathroom, they are out and to this direction. And please note that all sessions are recorded. So everything that you attend today is recorded. Slides and videos will be available about 2 to 4 weeks from now. You'll receive an email to where you can find all the information from all the sessions. So I'm Kitty Nix. I am Senior Practice Manager for the Federal Civilian Practice for Professional Services within AWS, and I am thrilled to introduce Gargi and Amy, who are here today to speak to you about implementing a data warehouse using AWS solutions and services in a hybrid environment. Amy was kind enough to donate her time from Fannie Mae, one of our customers. We love it when our customers come and share their stories, so thank you. Please, big round of applause to Gargi, who's going to start us off today.
Yep, thanks.
Thank you so much.
Yep, thank you, Nikki. No, I don't need that. Yep. Thank you, everyone, for joining us today here in this session, implementing a data warehouse on AWS in a hybrid environment. My name is Gargi Singh. I work as a solutions architect with a worldwide public sector team in the federal civilian space. With me co-presenting today is Amy, and she's a database engineering manager at Fannie Mae. So let's see, what do we want you to take away from this session today? The first thing I want to talk about today is, why do enterprises want a hybrid cloud? What are those reasons and some use cases where we see our enterprise customer going towards a hybrid cloud strategy? Then I'll talk about how you can create a data warehouse on AWS. What are some of the data design and what are some of the data design considerations that you should have when you're designing a data warehouse on top of AWS? And lastly, I would like to invite Amy to talk about how Fannie Mae is utilizing AWS products and services to create their own data warehouse on AWS. So let's start by talking about, why do enterprises want a hybrid environment? So when we talk to our customers, we see that there are certain use cases where they would require to run certain application on premises. Now, these reasons could be due to lower latency, where certain applications have interdependencies within one another. This could be because of certain legacy applications which haven't undergone a migration effort or modernization effort. We also see in the federal space that certain of our customers, due to compliance reasons, have to run applications on premises. We see that our customers utilize the cloud infrastructure and services to create DR strategy to make sure that they have a geological and geographical DR strategy where they can run certain parts of their applications on premises and keep a backup of these applications in different regions provided by our AWS. We also see that our customers recognize the value and the scalability and the elasticity of the cloud, but at the same time they know that not all applications can move at once to the cloud. They see that certain applications will go through certain modernization efforts, and it might take some time to reach there. So they treat this this hybrid cloud strategy as part of their phased migration of workloads, where they recognize certain applications that can start from scratch, or certain applications which can be migrated right now into AWS, into the cloud, and certain part of those applications are running on premises until they go through those modernization efforts. So what do customers want in a hybrid cloud environment? So our customers want to be able to run workloads on premises. They want to be able to run workloads in the cloud and utilize cloud services. They want a tight integration between these services. So they want to have the same security posture. They want to use the same identity and access management which they are utilizing on premises and take these capabilities into the cloud. And they also want to achieve this scale and elasticity without worrying about how they are going to provision new infrastructure or how they are going to buy new hardware. They want to dynamically scale up based on the resources and the applications. If they have a new resource-intensive application, they want to utilize the elasticity of the cloud to scale up during that application lifecycle and scale down when the application has done its job. So some of the use cases that we see our customers utilizing for a hybrid cloud strategy is they want to be able to integrate the different data silos. So there are different applications. Some of them can run on premises. Some of them can run in the cloud. And they are generating all these different kinds of data. They want to make sure that they have a way to integrate these different data silos at a single location and then do analysis on top of them to gain meaningful insights for their business so they can improve their business processes. At the same time, they want an integration between the identity and access management. So it could be the same way that they are managing their applications on premises, the same federation, the same SAML insertions, and they want to bring those capabilities into the cloud so that they can have an integrated way of managing applications which are running on premises, as well as applications and services which are running on the cloud. They also want to be able to integrate resource and deployment management. So they use the same tools which they are using right now on premises and bring those capabilities of deployment and managing the resources into the cloud with the tools they are already aware of. And we have seen customers use this hybrid cloud strategy as part of their cloud bursting capabilities. And what I mean by that is if you have a resource-intensive workload, which you are not able to run on premises because of provisioning new hardware, and it might take some time to get rack and stack those hardwares and get the application going, they can utilize the hybrid cloud strategy to then take these workloads to the cloud and elastically scale up or scale down as the workloads demand. And we have also seen our customer utilize this hybrid cloud strategy as part of their data center extension. So they are treating these different regions in the cloud as an extension to their data center. So they can run certain part of their application on premises and certain part of applications in the cloud. And with all these different applications which are coming up and all these different strategies, we see that there's a vast amount of data, and the data is increasing. This data can be produced by applications and services which are running on the cloud or application or services which are running on premises. And our customers want to be able to integrate all these different applications and services and the data they are producing at a single location so they can analyze and gain insights from that data. When we talk to our customers, we see that over the last 5 years, they have seen that the data has grown 10 into X times. And they want to be able to analyze all this data that is being produced. When I talk to my customers, we see that whenever we talk about creating a data platform, they tell that the data platform should at least live for 15 years. And it should have the capability to scale at a magnitude of thousands. So as the data demand increases and as the data is being produced, they want to be able to analyze all this data which is being produced. So when we talk about analyzing this data, we talk about what is the analytical pipeline for creating an application. And it all starts by the collect phase. You recognize what applications are producing this data. You see how are you going to collect the data. And we have a bunch of different options available on AWS that you can select from. Starting from database migration service, which helps you migrate your databases from on-premises into the cloud. If you have workloads such as object storage and you have massive amounts of data that you want to move, you can utilize our Snow family, which includes AWS Snowball and Snowmobile. If you have workloads which require streaming data or real-time applications and you want to collect real-time application data, you can use the Kinesis family. So that includes Kinesis Data Streams and Kinesis Firehose. And you also have the capability to have a direct physical connection between your on-premise data centers and AWS using Direct Connect, so you can move the data over the wire. So once you have recognized which applications are producing this data, are they on-premises or are they in the cloud, the next step is how are you going to store this data? Is it going to be an object store? Are you dealing with files or different kind of data types? So you can utilize Amazon Simple Storage Service for your object storage needs and Amazon Glacier if you have any archival needs. If you deal with file systems, we have different offerings in that department as well, starting from Amazon Elastic File System or FXX for Windows-based workloads. If you look at the different database offerings that we have, starting from the new services or the newer services which we launched, such as Amazon Quantum Ledger Database or QLDB, or time series database, which is TimeStream. And if you look at the more traditional RDBMS systems, such as Amazon RDS or Amazon Aurora, we have a bunch of different offerings to choose from in terms of how you want to move this data and how you want to save it on top of AWS. The next step in this pipeline is to recognize, is there any ETL requirements or extract, transform, and load? So as you're bringing in the new data, do you need to change the data types? Do you need to change it to a defined schema? Is the data you're collecting in an unstructured format? Do you want to convert it into a structured format before you do further analysis on top of it? So you can utilize AWS Glue, which is a fully managed ETL solution, or extract, transform, and load. And you can also utilize the data cataloging capabilities to see which applications produce what part of this data, so that you can have a holistic view internally to see, okay, this application produced this part of data, and I have a catalog for it, so I can maintain the access and management as well. When we talk to our customers, they want to consolidate the data being produced by all these different applications, and they want to create data warehousing solutions. So you can utilize Amazon Redshift, which is a fully managed data warehouse in the cloud. And I'm going to touch upon Redshift later on as we speak as well. But the last step in this analytical pipeline is, once you have done your analysis, once you have generated your defined schemas and you know what kind of analysis you want to do you want to do online analytical processes, or do you just want to do some ad hoc queries, you can utilize business intelligence tools to connect to Amazon Redshift, or the tools that we have available, such as Amazon QuickSight, which is a fully managed business intelligence tool. We have also seen our customers utilizing this analysis data sets that they create and feed them to machine learning workloads to create predictive analysis. And you can utilize Amazon Machine Learning or SageMaker to run your predictive analysis utilizing the data that you just analyzed. And we also have a bunch of third-party tools available on AWS Marketplace that you can choose from as well. So when we talk to our customers about data warehousing, they want to be able to consolidate all the different data sets that are being produced by these different applications, but at the same time, they want to elastically scale up or scale down their capacity based on their workload demands and requirements. They want to be able to modernize the current data warehousing architectures to scale up capacity as the application capacity needs, or as you get more concurrent queries, or you get more number of users accessing your data warehouse. So they want to be able to modernize the data warehouse. But what does data modernization mean? Our customers want to be able to scale to any amount of data. So they want to be able to scale as new data comes in, or as new applications start producing newer kind of data or newer types of data. They want to be able to work with different workloads, and they want to be able to scale to any amount of users without degrading the performance. They want to get consistently fast performance from their data warehouses, and they want to do it without managing the underneath resources. They want to utilize a service which is easy to use, and they don't want to waste time managing menial administrative tasks of maintaining the underneath resources. They want to utilize managed services. And another important aspect is for our customers is to not only the capability of utilizing the data warehouse, but also extend these querying capabilities using the same SQL, using the same SQL clients that they connect to, and extend these capabilities to their data lake, which they are creating on top of AWS. So let's now talk about how you can create data warehouses on AWS. But before I go there, let's talk about what are the few design considerations that you should have when you are creating a cloud data warehouse. So the first thing you want to think about is, how are you going to prepare your data sources? Is the data that is coming in, is it coming in batch processes? Is it coming in real time? How are you going to ingest this data which is coming in into your data warehouse? Do you have any extract, transform, and load operations associated to convert your unstructured data into a defined schema? What are your data quality requirements? How are you doing your data quality checks before this data goes into your data warehouse for further analysis? We have partner tools available and partner solutions available on AWS Marketplace that you can choose from for your data quality needs. And at the same time, do you have any auditing requirements? How are you going to manage who has access to, or which application has access to what part of your data? So these are a few things you should consider before you start designing your data warehouse. Do you have any nightly ETL jobs that you want to run? How are you going to manage your data transformations from different applications which are feeding in this data? Next I want to talk about is what does an enterprise data warehouse workflow typically looks like. So when we talk to our customers, the first step starts from recognizing what are your data sources. Are your data sources on premises or are these in the cloud? Once you recognize your data sources and the applications which are producing this data, the next step is how are you going to collect it? We have a bunch of different options to choose from. AWS Database Migration Service. We have Snowball or Snowmobile that you can choose from. AWS Data Sync, which automatically transfers your data from your on-premise systems into AWS with automation involved in it, so you don't have to go in and manually transfer or copy the data from your on-premise systems into AWS. Or you can utilize Direct Connect, which is an actual physical connection between your data centers and AWS, and you can transfer the data over the line. Once you have recognized how are you going to move this data, the next step in this pipeline or in this workflow is how are you going to save this data? And we have seen our customers utilizing Amazon S3 as their landing zone for all the data from their different applications. They keep the data in both structured and unstructured format under Amazon S3. And if you have any ETL requirements or you want to transform your data from one schema to another to feed into your different data warehouses, you can use AWS Glue, which is a fully managed ETL solution, or you can use Amazon EMR, which is an Elastic MapReduce service. We have also seen once the customers have done those ETL operations, they have transformed the data, the next thing is another staging area. So you can put the transformed data into Amazon S3, and that acts as your structured data or the staging area where you can now feed in this information to your data warehouse. And in this specific case, we have Amazon Redshift, which is a fully managed data warehouse in the cloud that you can utilize. And the last step in this process is to visualize. And we have seen our customers utilizing business intelligence tools such as QuickSight to generate those reports at the end of the day or at the end of the month and feed this information to their business processes to improve their business processes. When I talk to our customers, we also see the need to not only query the data which is sitting on their clusters or their data warehouse, but also query the data which is sitting in the raw shape or form underneath the storage. So they want to be able to extend those capabilities from the data warehouse to their data lakes or to their underneath storage. And you can do so by utilizing the Amazon Redshift Spectrum feature, which allows you to query directly data which is sitting on top of S3. So what is Amazon Redshift? Amazon Redshift is a fast, simple, cost-effective data warehouse in the cloud that not only gives you the capability to query data which is sitting on that cluster itself, but also utilize the Spectrum feature to extend those capabilities to your underneath data lake. You can utilize open formats such as Parquet, OCR, or Avro to analyze, utilizing the same SQL tools and the same SQL syntax that you are currently using. What Amazon Redshift gives you is the ability to get faster time to insight for all workloads or all different kind of analytical workloads, and it is powered by machine learning, columnar storage, and massively parallel processing capabilities. What I mean by columnar storage is that when you load the data into Amazon Redshift clusters, it is going to be saved by column basis and not by row-wise. It also gives you the capability to elastically provision new resources as your workload demands increases or decreases. And you also have the capabilities to extend these querying capabilities from the same SQL clients, from the same SQL to your underneath storage using the Amazon Redshift Spectrum feature. One of the important things I want to talk about is that it's 1/10 the cost of the traditional data warehouses. So what this gives you is the ability to try out new use cases. So what we have seen our customers do is, since it's under the same cost and the same budget, they are able to try new use cases and bring those new use cases once they are successful into their production workloads. When I talk to the customers, the most important things to our customers, the 4 most important things to our customers is that the data warehouse should have speed, simplicity, scale, and security. They want to get faster time to insight. They want their queries to perform better. At the same time, they don't want to do the undifferentiated heavy lifting of managing the underneath resources, but rather AWS take care of that. And at the same time, as the workload requirements increases, they want to elastically increase the amount of compute and storage they have on the data warehouse. And once if their workload demands decreases, they want to scale down as well. And at the same time, they want to utilize the same security posture and the same compliance policies which they have been utilizing so far and bring those into AWS Redshift as well. Now let's take a look at what does the Amazon Redshift system architecture looks like. If you take a look at this image, you will see that you are utilizing the same SQL clients and the same BI tools to connect to Amazon Redshift. If your applications have ODBC and JDBC compliant drivers, you can keep utilizing those to connect to Amazon Redshift. And how you connect to Redshift is that you connect to that green box or the leader node. What that leader node consists is, it is the SQL endpoint to which your BI tools will connect. It will store the cluster metadata. So all the metadata about the cluster will be stored on the leader node. And the leader node also executes the query execution plan. So it will make sure that the queries which you run on top of Redshift are executed equally on the compute nodes underneath. Talking about the compute nodes, these are the local columnar storage on which your actual data is going to sit. So when you load the data into the Redshift clusters, these are the compute nodes which will actually save the data. All the queries which are executed on these compute nodes are executed in parallel. So that's how it helps us achieve the massively parallel processing scale for Redshift. Each of these compute nodes will only execute the query on the amount of data which is stored on that particular compute node. So this is why we are able to achieve a shared nothing architecture, where each of the compute node is only taking care of the part of the query that it belongs to and the data which is saved on that compute node. If you look at the operations such as load, backup, restore through either Amazon S3, loading data from DynamoDB or EMR, each of these compute nodes will talk in parallel to the underneath service, henceforth increasing and maximizing the throughput for your applications. Now let's take a look at the compute node, dive deeper into what a compute node is. So a compute node is partitioned into either 2 or 16 slices. And you can think of each of these slices as a virtual compute node. It will have its own part of memory and disk space. At the same time, each of these slices will save data independently of one another. The leader node is responsible for distributing this data on each of these slices, and it will also execute the query execution plan where the leader node will distribute how the query is going to be executed on each of these different slices. These slices are responsible for the Redshift symmetric multiprocessing system, which allows Redshift to be a massively parallel processing system. Now let's talk about security. So security is built into Amazon Redshift. You would be able to achieve end-to-end encryption, both in transit and in rest. You can integrate Amazon Redshift with other AWS services such as AWS Key Management Service. So you can either utilize the keys which are generated by KMS and managed by KMS, or you can bring in your own keys to encrypt the underneath storage. You can also take benefit of the compliance that the service has achieved, such as FedRAMP, HIPAA, PCI, and others. Now let's shift gears and talk about what are a few data design considerations that you should have when you're designing your data warehouse on top of AWS. But before I go into what are the design considerations, let's talk about some of the anti-patterns where Redshift would not be an ideal solution for you. If you have data sets which are less than 100 gigabytes, you would not see much benefit of utilizing Amazon Redshift because it was built for scale and it's built to be a massively parallel processing system. So for workloads which were less than 100 gigabytes, you won't see much benefit of utilizing Amazon Redshift. If you have applications which deal with online transactional processing or OLTP operations, a more traditional RDBMS or a NoSQL database would be effective in these kind of situations. If you have unstructured data, we have seen our customer getting maximum throughput and maximum efficiency out of their Redshift clusters if they have a defined schema. So if you have unstructured data, you can still utilize your data lake as part of Amazon S3 to keep that unstructured data and utilize the Amazon Redshift Spectrum feature to query data directly from the underneath storage rather than worrying about loading this data into your Amazon Redshift clusters. So now let's talk about what are a few of the design considerations that you should have when you are creating a data warehouse. So the first thing is, are you using the optimal data types? So are you using Avro, Parquet, or other open file formats and utilizing their compression and partitioning capabilities to lower your cost and improve your efficiencies in terms of your querying capabilities? Another thing I talk to my customers is, how are you loading this data? What are your strategies around loading the data into your Redshift clusters? There are multiple ways that you can load the data into the Redshift cluster, but one of the ways is to use the copy command, which will copy the data sitting on Amazon S3 into your clusters. One of the things I talked to them about is that utilize the Redshift's massively parallel processing capabilities. Each of the compute nodes is divided into slices. So in this particular example, you see I'm using a DC2.8x large compute node, and it has 16 slices. So if you have an input file, and you divide that file into 16 pieces, each of these slices will execute the amount of data that has to be loaded by each file. So you can essentially increase the throughput and maximize your throughput by matching the number of slices that you have in the cluster to the number of input files, because each of the slices will operate in parallel, and that will increase the throughput for your loading operations or your backup operations. Another thing to consider is how are you distributing the data? Do you have a good distribution style? What kind of distribution style you are selecting when you are moving the data into your Amazon Redshift clusters? There are multiple different distribution style available. One of them is the distribution keys, where you select a good distribution key, and what happened underneath the covers is that we hash the value in each of those columns, and the value belonging to the same hash will go on the same compute node and on the same slice. The other distribution style is distribution style all, and this particular distribution style is good for tables which have less than 100,000 rows, because each copy of the entire table will sit on each of the compute nodes. And the last distribution style is distribution style even, where as the data is coming in, we are going to distribute the data in a round-robin format. So these were the things that you can do to improve the efficiencies of your Redshift clusters, but underneath the covers, we are also working to increase the efficiency of the service itself. Now let's talk about a few of the recently released features. We recently released a new compute type, which is the DC2 or Dense Compute Node 2, which increases the performance of your Redshift clusters from the previous generation of DC1 2 into X times at the same price. So you can start using, even if with a small migration from one compute node to another, you would see 2 into X time benefits of your performance being increased. We have also worked on increasing the efficiency of result cert cache. And what this does, if you have sub-second repeat queries which you are running at a frequency, which you are running at a very high frequency, we will cache the results of those queries, and we will, next time the query is run, we will feed the result from these caches instead. And this frees up thousands of compute hours for your Redshift cluster to perform other operations such as ETL or ingestion operations. Another feature I want to talk about today is short query acceleration. And what this helps you to do is, we will use machine learning classifier underneath the cover to see the execution time of each of the query which you are submitting to your Amazon Redshift cluster. And if we see that within your Redshift queues, if there are shorter running queries waiting behind the longer running queries, we will dynamically route these shorter running queries to an express queue, and we will provision resources for these shorter running queries to be executed first. And once the execution of these short running queries have been done, we will go back to the longer running queries and give all the resources for those queries to be executed. This feature is now available, and you can start going to your AWS Management Console and start utilizing the short query acceleration by just a single click of a button on the AWS Management Console. The next feature I want to talk about today is Amazon Redshift Elastic Resize. What this allows you to do is scale up or scale down your Amazon Redshift clusters and add more additional compute nodes to your clusters if you see that your workloads are demanding more resources, both in terms of the compute capabilities as well as in terms of the storage. So you can add more clusters within minutes to your Amazon Redshift cluster. You don't have to worry about how the data is going to be distributed into this new configuration, because we will take care of underneath the covers when you add those new compute nodes to the Redshift cluster. There is a minimum transition time, so it usually takes up to 1 to 5 minutes to bring up those new compute nodes, and you can then utilize the queries which are going on in your Redshift clusters. You can quickly scale up. So what we have seen our customers utilize this feature for is, for example, on the month end or every day at night, you have a resource-intensive ETL query, or you have a storage-intensive ingestion job. We see our customers utilizing the Elastic Resize to elastically resize and increase the compute capabilities and add more nodes to the cluster. And once that job is complete, they go back to the optimal cluster size, which is required to run their additional queries. Another feature I want to talk about today is concurrency scaling for burst user activities. What this feature gives you is, For example, on a Monday morning, you come in and all your analysts are typing in reports and they are submitting queries on their Redshift clusters, and you start experimenting waiting time on your queues. What this feature will allow you to do is we will automatically bring up transient clusters to the main cluster, and we will distribute these queries which are waiting in the queues. If we see there is more than 60 seconds of wait time on your queues, we will automatically bring up these transient clusters, and we will distribute these queries to these transient clusters. Once the queries have been executed, and once there are no more queries waiting in the queues, we will take these transient clusters away, and you are only paying for the time the transient clusters are actually running those queries. What this allows you to get is consistently fast performance, even with thousands of concurrent queries, because now your clusters are not waiting to execute these queries, but rather these transient clusters come into play, and we distribute the queries so all the queries are running concurrently for you. One of the important features that we have seen when we talk to our customers as well is this feature is essentially free for 97% of our customers, because for every 24 hours your main cluster is in use, you accrue 1 free hour of concurrency scaling credit. Now let's shift gears and talk about Amazon Redshift Spectrum and what are the features that you can take use of by utilizing this Spectrum feature. As I mentioned earlier, Spectrum allows you to query the data sitting directly on top of your Amazon S3 buckets as part of your data lake. So you are able to use the same SQL syntax and the same SQL clients which you're using in your Amazon Redshift clusters and bring those capabilities down to your data lake, so you don't have to worry about loading the data into the clusters, doing ETL transformations before you can actually start reading the information from that new incoming data. What we have seen our customers use this feature for is if you have archival needs, so they keep the archive data as part of their data lake, and they utilize the Amazon Redshift clusters to keep the newest data. But for example, if you want to go back and query the data which is 2 years old, you can utilize the Spectrum feature to go back and query only that part of data and only access what is required to be accessed for making use of one query. This particular feature gives you the capability to scale your compute separately from your storage. So you can create your data lake, and you can scale your compute separately based on how much compute capacity do you need to run your regular workloads versus how much compute capacity you need to run a query which will run once in 2 years or once in a year. You have the capabilities to utilize the open formats such as Parquet, OCR, Avro, and other file formats to query data directly utilizing the Amazon Redshift Spectrum feature. We have also worked to improve the performance of Spectrum, and what we are going to implement soon is that the ability to not only utilize this open data source or open file formats such as Parquet and Avro, but the capability to unload the data from your Amazon Redshift clusters onto your underneath storage utilizing the unload to Parquet option. And we are also working to increase the execution time of each of the Spectrum queries by working on the feature which is going to release pretty soon. Is called Spectrum Request Accelerator. Now if I go back and wrap it up in terms of what are the different things that we are doing to improve the performance of Amazon Redshift as a service, you can see the foremost thing that value to our customers is speed, and we have recently introduced new services such as elastic resize and concurrency scaling features within Amazon Redshift. If you look at scale, we have introduced Spectrum Request Accelerator and unload to Parquet options. And if you look at simplicity, we have released new features such as auto vacuum, which will automatically run the vacuum operations on your cluster itself when we see that the cluster utilization is less. So you don't have to run those vacuum operations again and again to delete the rows which were marked for deletion. We have also introduced the auto analyze, which will take a look at your cluster automatically and generate the performance reports of how much execution time is happening in your clusters and how much resources your cluster is consuming. And at the same time, we have introduced the auto data distribution. So we will pick a good distribution style for your clusters by looking at your cluster utilization and pick a good distribution key to automatically distribute the data on your Amazon Redshift clusters. When we talk to our customers, we see that not only they want the service to be secure, but they also want to have tight integration with other AWS services. And one of that integration that we are going to launch is with Amazon Lake Formation once the service is generally available. Now I'd like to invite Amy from Fannie Mae to talk about how they are using AWS product and services and how they are creating their own data warehouse on top of AWS. Thank you.
Good afternoon, everyone. My name is Amy Chen. I'm a technical manager in Fannie Mae. I lead database migration as well as database engineering to AWS. So today I would like to introduce our journey, data warehouse journey to AWS. First, let me tell you a little bit about what Fannie Mae does. We are the leader in providing housing market for housing finance for home buyers and renters in the United States. We provide access to affordable home financing in all markets at all times. We fulfill our mission by providing liquidity to the market. Home ownership in the United States are at 64%, and Fannie Mae provides 36% of home financing. Our financing makes sustainable home ownership for millions of Americans. So our data warehouse journey starts about 4 years ago. Our data warehouse stores a system of records. The data in our data warehouses serve analytics communities for research and data science. The data in these data warehouses are also used to generate regulatory reports and financial reports. We have several legacy data warehouses, and we are consolidating these data warehouses into enterprise data warehouse. So far, we have been very successful in our data warehouse strategy, but that creates new challenges for us. Now, with the data warehouse consolidation, we see 6 times to 20 times of transaction in the last 18 months. With the digital transformations, we see more activities happening in our data warehouses. We see 3 million queries per month, and then we see 4 times of data growth. Successful user adoption means we have more user base coming to our data warehouse. We see 100 to 1,000 users in the last 3 years. Then from the application standpoint, we have 80 applications that come into our data warehouses, and then we are planning to onboard more than 100 applications to our data warehouses. So that leads to the concurrency issues and then some of the scalability issues. So to mitigate some of these issues, we have done tried to do numerous things. First, for the ad hoc user queries, we have to terminate their ad hoc SQLs if they are running too long. And for the application jobs, we work with application teams to prioritize the critical jobs to make sure that we remediate and then reduce the resource contentions. So we have been constantly doing that. And that was not good enough, so what we did is we moved our ad hoc users as well as reporting to a separate data warehouses. And then we use the nightly data restore to sync up the data to this reporting data warehouses. So in some cases, we also need to do our application enhancements in order to make the new data attribute available to our business users. So time to market is our concern too. So what we really need is we need the self-service capability where our business users is able to create a data set by themselves without needing the application enhancements. What we also need is, as I mentioned, we have more data coming to our data warehouses, and we have ad hoc users and applications. Sometimes those volumes are not predictable. So we need to have ability to dynamically scale in order to meet those increased data volumes. We also want to have the data sharing across multiple teams, so there is a single source of records from the analysis result as well as our reporting. Our data is separately maintained by different business domain, and we would like to have the cross-domain access so that all these data are available to our business users. Finally, as I mentioned, we have more users and more application onboarding to our data warehouse. So we need to have the ability to scale to meet our sudden spike of workload and then to our ad hoc queries. So what we did is we turned Redshift to address these challenges. First, the Redshift has some numerous features that Gargi mentioned before. And I would just like to mention several of these features that we use to mitigate our challenges. With the Redshift spectrum, we're able to query the data directly in our S3 and using the SQL, which most of our users are familiar with. And this feature cuts down the time or eliminate the data loading. We're also able to share the data across the teams as well as across a business unit without making a data copy. We can also join the data in Redshift as well as the Redshift spectrum together and still using the Redshift query optimizer even though part of the data are not in the Redshift cluster. Next is the concurrency scaling features. As I mentioned, one of our issue was a concurrency. And to this concurrency scaling feature address our concern. Now with these features, Redshift will automatically instantiate the new transient cluster in the background to meet our sudden spike of workload. And these transient clusters are transparent to our users, and these clusters are removed once the workload is completed. Now, with this feature, we also see there's less number of nodes needed to complete our existing workload. And then I'll show you later what I mean by that. For every 24 hours a main cluster is up, we get 1 hour of credit. So again, that is going to the cost saving. So we spend numerous times that I mentioned that we have to work with application teams to prioritize our workload. We also spend time on auto vacuum for the vacuum and some other maintenance job in order to make sure that our user can run our query optimally. So with the auto workload manager and then auto vacuum features that Redshift providing, this saves our administration cost, effort, and then our DBAs is able to devote those time to do more database engineering. There are other 2 factors that we consider Redshift for. We're building a data lake in AWS, and Redshift is part of the AWS ecosystems. So what that means is it enables us to share the data within the data lake and within our AWS ecosystems. The other thing is the Redshift constantly adding new features and it has a rich roadmap. So here's at the very high level how our existing on-premise architecture look like in our data warehouse environment. We have upstream applications which feed the data into our data warehouse. And we have a downstream application also getting the data from our data warehouse. Now we have a reporting that running using the popular BI tools, and those are accessing our data warehouse. Then we have ad hoc users that access our data warehouse directly and then running the ad hoc queries. Now going to the data warehouse, data lake, our strategy is having all these data available in S3 first. So there's numerous ways to hydrate these data in AWS. So in this data warehouse use case, what we did is we developed our custom solutions. And we extract the data from our data warehouse, put it in a flat file, and then we move those data over to S3. Now, from S3, we can do numerous things using numerous different services based on the different use cases. For the data we need to do further transformations, we use EMR. And for user, we just want to do a simple query, and then we want to access the raw data. They don't want to bring up the Redshift on their own. For those users, they use Athena. Then our regular Redshift, our regular data warehouse users, they will be, when they move to cloud, they will be using Redshift. So with this approach, we are enable our applications as well as our business users to migrate to AWS in phases. And with this approach, this also relieves our scalability issues on premise. So here are one of the benchmarks that I would like to share with you. In this benchmark, what we did is we used the concurrency scaling features, and the blue bar represents the Redshift 16 nodes, and red bar that represent Redshift 8 node with concurrency scaling feature enabled. Then we run our 10 most executed SQLs from anywhere from simple to complex SQLs. And we put the results side by side. So as you can see in this benchmark, the Redshift 8 nodes with concurrency scaling features is actually achieving similar or better performance than Redshift 16 node. Here is another benchmark that we did. This time we used the same number of nodes. Blue line represents a Redshift 8 node without scaling features. And red line represents a Redshift 8 nodes with a concurrency scaling features. Then what we did is we run one of the compressed query that we have, which does 5 table joins. And we run this query anywhere from 1 to 100 concurrencies. So as you can see, without concurrency features, the execution time of these query increases as the query concurrencies increase. Now with the concurrency scaling features enabled, the execution time relatively stay flat, meaning the performance did not degrade as the query concurrency increases. So here are the couple of lessons learned. First is choose the node type wisely. So we have the DC2 dense compute as well as the dense storage, different node type. And for most of our workload, the DC2 work well for us because most of our workloads are read intensive. But for some of our use cases where we have a write intensive, heavy write, in those cases, DS2 we found, in those cases, DS2 found a better for us. And if you're using DC1, still using DC1 today, I really recommend you to take a look at DC2. When we moved DC1 to DC2, we saw a significant performance improvement. Second, on the concurrency scaling features currently works for read-only queries. So what that means is your write transactions or your read queries that creates temporary tables, those will remain in the main cluster. Then your read-only queries will be distributed to the transient clusters to continue to perform your queries. And more nodes do not always yield a better performance. So what in one of our use cases, once we cross a certain number of nodes, the performance actually degrade. So that's what we mean by that. Find your sweet spot. In other case where we have the 8 node, initially we have an 8 node cluster, and then we increase this to 12 nodes, right? And we yield 10% more performance gain. So the question is, does it worth it? So people ask, does Redshift perform? Or can Redshift perform to what I want? So I would like to rephrase the questions to how much do I want to pay for the performance I want to gain? So when you're looking for performance, always look for performance plus cost. And I mentioned about the concurrency scaling feature earlier. So what about if I have a lot of writes? So for that, we have looked at elastic resize, and that gives us more compute power temporarily for us to be able to complete our data load faster. And lastly, another thing I want to mention about is the functional test. So make sure that you have the meaningful data volume for your functional test. In our early days, when we test with our Redshift, we test with a very small data sets. And that did not really see the result that we wanted, and that it was because we are using our data volume was too small. So just make sure that you have the meaningful data volume when you're testing your functional. Now, in terms of performance testing, like I mentioned, need to find your sweet spot. So for that, we did numerous different tests. We try a different number of nodes, like I mentioned, and then we try with and then without concurrency scaling features, right? And also, we try with a different number of concurrency query concurrencies. So user will give us, here's the number of concurrency that I want, but not always the concurrencies that you have been running in your current system today translated to that's what you're going to see in the Redshift. So we use a different number of the concurrency to test and make sure that we find the optimal configuration to start with. Now, once you start your Redshift with the configuration you want, if you need to adjust, right, adding more nodes or need to resize, then that's available for you at the tip of your finger, available to you there. And finally, I would like to mention about the non-functional requirement. Like I mentioned, we are building our data lake in AWS. And so ease of integration with various AWS services are very important to us, besides performance. And also, we are very cognizant about where our data goes. And with the query, we can query directly from our S3 bucket. This is a great feature for us. And then also, having our data in our account is very important to us. So with the Redshift and Redshift Spectrum, the data will stay in our account. So with that, thank you very much for coming today. If I can ask you to fill out the survey and let us know your feedback, that would be great.